gentlemen, real transformers or practical transformers. They differ from the already studied ideal transformer in foreign ways. Essentially, the assumptions we made about the real transformer aren't true. Real transformers, their windings have got resistance. In the ideal transformer, we assume they haven't got any. Their cores are not infinitely permeable, so they won't take an unlimited amount of magnetic field. Eventually they'll saturate. Yeah. The flux produced by the primary is not completely captured by the secondary, i.e. their leakage flux, and equally the flux in the secondary is not all captured by the primary, so that linkage is not perfect as leakage flux in a real transformer. The iron core, we assume there were no losses, but actually iron cores produce eddy currents and hysteresis losses. There are losses due to magnetising the core and demagnetising it twice a cycle. Yeah. So these losses contribute to a temperature rise of the transformer. That's why they heat up, and that's all power loss. So what we need to do is develop a model of a real transformer that will take into account these loss attributes, the losses that are experienced by a real transformer. That's what we're going to look at. So, ideal transformer with imperfect core. So we're going to consider a situation where transformer is open circuit. Okay, if the transformer was ideal, the secondary side was open circuit, no current flowing, right? Then there'd be no current flowing in the primary either. That's not the case, because there's a magnetising current and a current due to the eddy current losses in the core. So the core of a real transformer is not ideal. It's not entirely permeable to hysteresis losses and eddy currents flow. This means a real transformer is open circuit. There will be a current flow in the primary coil called I0, IO, but not in the secondary, I2. This current is represented by two currents, IM and IR. These two currents, parallel currents, IO being down there, and that's made up of IR through a resistance and IM through a magnetising coil. Yeah, representing the magnetising current. So the resistors representing the eddy current losses, and the inductors representing the magnetising current losses. Yeah, it's got to magnetise that inductance regardless of whether you're drawing any current in the secondary. Yeah. So there it is in writing. R represents the iron losses and the resultant heat produced, which causes the in-phase portion of IO to flow, called IR. So there's IR, the in-phase portion. Okay, the two voltages off-load are in phase with each other. Yep. Right, happy with that? I've got more writing on my page. You got more writing on your page? Right. XM represents just have a look and make sure it's not on the next page. No, it's an example. Magnetizing reactance. Of the primary coil. That produces the primary flux indicated in the middle of the transformer there. Never remember my Greek letters. Is that a capital theta? I think it is, isn't it? I don't know, not sure. This requires a magnetizing current IM that is the out of phase component of IO. Yep. So that is this current down here. The two together gives us the total primary current IO flow in there. So there's IR, IO, and IM in a phasor diagram. Yeah. So IO is a resultant complex current. So the result and is a complex current IO as shown in the phasor diagram and is called the exciting current. Christian will come across the term excitation, no doubt. It's generator plants, slightly different term there, but it's still the current that excites the magnetism into the rotor, isn't it? Yeah. Okay. So it's a general kind of term for a current that produces a magnetic field as an exciting current. That doesn't mean that's wonderfully exciting to experience. Right? So that's the kind of theory around that iron loss through eddy currents, heating the core up, and the magnetising, producing the magnetic field in the primary winding. That's represented by two parallel components in the primary side of the transformer model. Yep. So that model at the page is a model of real transformer, or part of the real transformer. We got a bit missing yet, right? But it's effectively the offload representation of a real transformer. So let's have a look at an example problem. Large transformer operating at no load draws an exciting current of 8 amps. When the primary is connected to a 400 volt 50 hertz source. From a wattmeter test, it is known that the iron losses are equal to 500 watts. P loss equals 50 watts. Oh, hang on, 500 watts. Can't read me own writing now. 500 watts. Calculate the reactive power absorbed by the core, the value of Rm and Xm, the value of IR, Im, and IO. Okay, so where are we going to start? A. Reactive power absorbed by the core. What can we calculate with what we know? Let's just put, what I'm going to do on the diagram is just add these representations of R2 losses. Yeah. And that's where IO is going to run. Yeah. That's IR. And that's going to take IM. Yeah, go on, Christian, sorry. Yeah. Yes, because we got current and voltage from the generator. So the parent power, S, is equal to EG times I, and that's actually IO, isn't it? I don't know why I've asked you to find the value of IO here, because that's actually given to you. That's the only current flowing, alright? IO. So that is 400 times 8 is 3,200 VA. Yep. You're given in the question that the iron losses in core P is equal to 500 watts. So how can we get the reactive power? Yeah, we've got a triangle here with 500 there, 3,200 there. We want this one, Q. So we can go Q is equal to, and that's QM is equal to root S squared minus P squared. That's root 3,200 squared minus 500 squared equals. That's that's due to the magnetising current in it. That's due to the exciting current. You don't really need a subscript here because there aren't any other Q's contributing. But and I got 3161 var. Alright? So, B. What did B say now? Yeah. So let's find the impedance of iron losses. Can you see a way that we can find RM with the information that we know? Look at the diagram. In terms of RM, what do we know that we can use? Not all of IO is flowing through it, is it? We've got some of IO going there, some of IO going there. So current we can't use because we don't know which is which. Yeah, we can't find it because we don't know the value of these two components. So we can't use power and current to find, current and voltage to find. We know the power's associated with that, isn't it?
Yeah, that's power.
We know power, and we know E. Yeah, don't we? So we can do it from P is equal to E squared over R, can't we? Yeah. RM is equal to E squared over P. That's 400 is our voltage, is it? Yeah. Oh, hang on. What? That's wrong. That's I that's going to be that, isn't it? P is E squared over R, isn't it? Yeah? Yeah? Yeah, but that voltage, Christian, they're in parallel, remember. So you've got that 400 volts across both the resistance and the reactance. Yeah? Agree now? Yeah. So that's 400 squared over 500. I got 320 ohms. Had me worried there for a minute that I got a major mistake in my notes. Equally, magnetising reactance of core XM is equal to, again, E squared, at this time, over, Q. Believe me or not? So that's 400 squared over Q, which was 3161. 50.6 I got. Please check it, because you never know. That would automatically have an angle of 90 degrees if we needed it. Yeah. That's yours, is it? Yeah. Okay. And then lastly, C. The current IR is equal to E over RM. 400 over 320. 1.25 amps. And IM is E over XM. 400 over 50.6 equals 7.91 amps. They don't add up exactly to 8. Why? Not in phase with each other. Yeah? IU should equal IR squared plus IM squared, all square root, shouldn't it, by Pythagoras? Because they're 90 degrees out of phase with each other. So it's a square root of 1.25 squared plus 7.91 squared. We should get about 8 amps then. So that's an analysis of transformer open circuit, where we've got a current flowing because of a parallel and resistor and inductor, with a resistor representing the iron core losses, power loss, and the inductor representing the exciting current that magnetizes the core.